This is PreCalculus 12, Chapter 5.2. This time we're going to be analyzing exponential functions, and what we mean by that is transforms. Okay, so we have y minus k equals c times a to the power of d x minus h in brackets, or we can look at it this form, y equals c times a to the power of d times bracket x minus h plus k. And if we were looking in the function format, we would be looking at almost the identical thing. We're just changing the variables a bit. And we are replacing A and we're replacing B. And the reason for this is because A is the base. So we can't have two A's in a formula or equation that mean different things. So we have to use new variables. Okay, so C is now vertical scale and flip, D is horizontal scale and flip, H is horizontal shift, K is vertical shift. And we're still using XY goes to X over D plus H and CY plus K. Okay, this is the pre-image, this is the image. And we always start with the easiest point, and that happens to be y equals a to the power of 0, because this equals 1. So let's look at our example. Y equals 1.3 to the power of x. This is transformed by y equals 2 times 1.3 to the power of 1/3, bracket x minus 4, bracket. So we have a vertical stretch, and we have a horizontal stretch. Remember, we're dividing by 1/3. That means we're multiplying by the reciprocal, which means we're multiplying by 3. And this is a right shift. And this is down. Okay, and if we use a table of values, we have x, we have 1.3 to the power of x, and we have our transformed. So there's not a lot of grid points on this one because we have a decimal value here, and we can see decimal values here. So we can use a table of values or we can plot manually. Let's look at some points. This is 0, 1. We need to stretch this by 2, and stretching horizontally won't move it. Then we need to move right 4. I'm just going to put a tick mark here. 1, 2, 3, 4. Put a tick mark here. And we're going down 3. 1, 2, 3. And we're going to put a dot because this is our final answer. And let's do the next point in a different color. Okay, so we're doubling this. So that's here and a little bit more. And I'm going to put a tick mark there. And we're stretching it by 3. So this is 1. It's going to go to 3. Now we're going to move right 4. 1, 2, 3, 4. And we're going to move down 3. 1, 2, 3. And a dot there. Okay, so we can't go right anymore because this is going to be off our grid. So let's move left. Use purple this time. We're going to double this. That's roughly there. And we're going to stretch it from -1 to -3. And we're going to move right 4. 1, 2, 3, 4. And we're going to move down 3. 1, 2, 3. And now we can just draw a line through those points. Okay, because these are tick marks that are different than the dots, I won't confuse the two. We could have done another point here, but this is sufficient to show our curve. And let's look at something different. Determining an exponential function using tables. So we have two values. They're consecutive values. So if we're going this way, we do 18 divided by 6, that equals 3. So 18 times 3, that equals 54. If we go this way, we do 6 divided by 18, and we get 1/3. We simplify that. And that's the same as dividing by 3. So 6 divided by 3 is 2. And 2 divided by 3 is just 2/3. Okay, if we use the 0 table value, we can come up with our function y equals 2. So that's just taking the y-intercept. We take the ratio, so we take this ratio, it's 1/3, and to the power of x. Okay, let's do that again. So in this direction, it's 12 divided by 24. That equals 1/2. 12 times 1/2, that equals 6. Now we take 6 times 1/2, that equals 3. And then we do 3 times 1/2, that's just 3/2. Again, we're going to look at the 0 value, the y-intercept. That gives us y equals 3. And we need to go forward. So this is 24 divided by 12, that equals 2. We always have to take the forward value, not the backwards value. And that goes up here. We have 2 to the power of x. Okay, initial value problems. These are called growth decay problems. It'll be growth or decay, but not both. So we want to write this in a slightly different form. Y of t equals yi r to the power of k t minus ti. So how does this relate? This is our c, this is our a, this is our d, and this is our h. And what we're doing here is this is similar to slope point form. If we know A and D, all we need is one point, which is HC, or TIYI. Okay, to set our function. So the A and the D are kind of like our slope, and then our TIYI is our point. So yi is the initial value. If ti equals 0, then we usually denote ti equals t0 or t naught equals 0. And if ti doesn't equal 0, then it's just our specified value. Specified value meaning our given point. So k, we can think of it as the reciprocal of the time it takes for the ratio to change a specific amount. For example, if something doubles every 3 hours, then r equals 2 and k equals 1/3. Okay, so it takes 3 hours. So we take the reciprocal of the 3 hours and we get k equals 1/3. R is the ratio that the value changes. And percentage change needs to be converted to a ratio. Ti is the offset to the initial value if it's not at time 0. Again, this is our point that we're looking at to define our specific equation. So you should also note that yi, if it's a percentage, don't change it to a number. Because that's our units. We can have y as a function with a percentage. However, the ratio, this one needs to be converted to a number. Okay, let's look at some examples. The amount of light reflected off the mirror is 97%. How much light is remaining after 5 reflections? So R, we have 97 over 100. Remember, this is a percentage. We need to change it to a number, so it equals 0.97. K is equal to 1 because it takes one mirror to reduce it down to 97%. There's no time involved as well. It's per mirror. Ti, well, at time 0, we know the value at time 0. It doesn't specifically say, but it's inferred. At time 0, we have all the light, which means it's 100%. And don't convert to number. And t, this is the t that we want to evaluate it at. So it's just t equals 5 mirrors. So yt equals 100%, and our ratio is 0.97, and we can leave out the 1 because 1 times anything is itself. Come up with our equation. This is our equation. If you're asked to find an equation on a test, you need to have your parameter here and here. And then we say y of 5 equals 100%, 0.97 to the power of 5. And that gives us approximately 85.9%. Let's take a look at another example. A certain bacteria doubles in population every 4 hours. If the initial population is 500,000, what is the population after 10 hours? Okay, so we have 500,000. Ti is 0. Okay, the initial population is. So that's telling us the initial time is 0. And we want to evaluate this as t equals 10. And we're talking about double. Double means 2. And k is every 4 hours. So we take the reciprocal. We have 1 over 4. And we write our equation out. Yt equals yi r to the kt. And this is 500,000. 2 to the power of 1/4 t. So we have y of 10, 500,000 times 2 to the power of 10 over 4. And this is approximately 2.83 million bacteria. Okay, if you're not sure of your formula, you can always test it. And we don't need a graphing calculator to test this. So you just plug in 4. So does y of 4, does it equal? So if we're testing something, we put an equal sign with a question mark above it. And it should equal 1 million at 4, because that's double of 500,000. Okay, so we plug this in. 500,000 times 2 to the power of 4 over 4. And this becomes 1, so this is just 2. 2 times 500,000 is 1 million. The other thing we can look at is this is just times 2. Times 2 means a double. Okay, let's look at a harder example. And again, on a test, it's your test. You're allowed to write, underline, highlight, whatever you need to do to pick out keywords. Bacteria doubles. R equals 2. Every 3 hours. K equals 1/3. In the 8th hour, this is a specified time, so this is TI. There are 1,000 bacteria. This means that this is YI. So this is our specified time and our specified value. And then we have our questions. What is the equation for the bacteria growth? What is the initial population? When will the population reach 9,000? Another way of saying this is at t equals 0. Okay, so it's easy to write our equation now that we've picked off our values. Y of t equals 1,000, and our R is 2, and our K is 1/3, and we have t minus Ti, which is 8. Okay, so this answers 1, 2. We just plug in 0. 1,000, 2, 1/3 of -8. Let's plug this in. 1,000 times 2 raised to the power of -8 divided by 3. We get approximately 157.49. You can't have 0.49 of a bacteria, so we round down. Even if we had 0.8 of a bacteria, we still round down because you can't round a bacteria up. So 157 bacteria. And we'll call this 3. And we have an unknown, so we'll call it C. Y of C equals, and that's 9,000. And we have 1,000, 2 to the power of C minus 8. And we'll have Y1 on the calculator here and Y2 on the calculator here. So on the calculator, we use intersect when we have Y1 and Y2. So we know our answer is 9,000, so we should set our Y min to 0 and our Y max to 10,000. So our range is going from 0 to 10,000. If you set your scale to 1000, you get nice evenly spaced dots here rather than a solid line. We enter 9000 and we enter our y2. They intersect here. And for your domain, you can leave it at 0 to 10, and then you'll see that this doesn't quite cross, and then you'll adjust it accordingly. And it works out to 20 for this particular problem. And we see that we have 17.509. So our answer is 17.51 hours. Question is, do you round up or do you round off? If rounding off means you round down, you won't actually get 9,000. And depending on your teacher, that might be good enough or not. But I say the right way to do this is to round up. Otherwise, you are short bacteria. Because whoever heard of tall bacteria? Okay, that was a bad joke. Specified value is at a point. So it is similar to slope point form, which I mentioned before. So if you don't recall slope point form, please watch the additional video on slope point form. And that completes this lesson.